For 7 decades, physicists and engineers have pursued a single, highly specific goal: replicating the nuclear reaction that powers the sun and sustaining it inside a laboratory on Earth. Housing a miniature star requires immense physical infrastructure. You have to construct a vacuum vessel like a Tokamak, a massive, curved, heavily engineered chamber designed specifically to isolate the reaction from the outside world. The most viable fuel for this process consists of 2 specific hydrogen isotopes. The first is deuterium, which is extracted directly from seawater, where it exists at a ratio of about 1 in every 6,400 hydrogen atoms. The second is tritium. Look at this molecular breakdown of the reaction. When you force a deuterium and a tritium nucleus to fuse, they reorganize into a single helium nucleus and a high-energy stray neutron. That single event releases 17.6 million electron volts of energy. Because of how precise the conditions for that collision must be, the process has an inherent safety limit. It is physically impossible for fusion to run away. If the containment system fails or the plasma loses its shape, the entire reaction simply halts within seconds. There is no meltdown scenario. We have an inexhaustible fuel supply from the ocean and a reaction that naturally extinguishes itself. The true barrier to commercial fusion power is the extreme extremodynamic physics required to force those nuclei together in the first place. To fuse, the fuel must reach temperatures above 100 million degrees Celsius, roughly 6 times hotter than the sun. We have to push the temperature that high because we are working on Earth. We cannot replicate the crushing, inescapable gravitational pressure of the sun's core, so we have to substitute that missing pressure with immense thermal energy. Matter heated to 100 million degrees enters a state known as plasma. At this threshold, the kinetic energy is so violent that electrons are literally stripped away from their atomic nuclei. What remains is a super-hot, electrically conducting cloud of particles. This plasma is so hot that it will instantly vaporize any solid physical material it comes into contact with. You cannot put 100 million degree plasma in a physical box. We have to engineer massive machines capable of caging an incredibly volatile substance without ever actually touching it. To hold the plasma in place, engineers rely on 2 distinct architectural strategies: magnetic confinement and inertial confinement. Magnetic confinement devices, like Tokamaks and stellarators, surround the vacuum vessel with high-temperature superconducting magnets. These magnets generate intense, overlapping fields that squeeze and suspend the conducting plasma cloud in midair. Inertial confinement takes the opposite approach. Instead of suspending a continuous cloud, facilities fire highly synchronized arrays of massive lasers at a tiny, spherical fuel pellet. The beams hit from all directions, compressing and igniting the target before the physical matter even has time to fly apart. These specialized geometries represent decades of heavy engineering trial and error. Navigating the unpredictable fluid dynamics of a burning plasma has historically required immense bespoke hardware built at national scale. Recently, highly capitalized private companies have spun out of these legacy programs to pursue advanced variants, engineering compact magnetized target devices and field-reversed configurations. Superconducting magnetic coils and stadium-sized laser arrays both serve one ultimate mechanical purpose: substituting for the gravity of a star. To understand exactly how close we are to making this a power source, we have to look at the laser target bay at the National Ignition Facility. Here, inertial confinement experiments are conducted on microscopic fuel pellets. On December 5, 2022, the NIF crossed a historic physics threshold known as scientific ignition. For the first time in a laboratory, a fusion reaction produced more energy than it took to ignite it. This chart compares the exact energy transfer. The NIF delivered 2.05 megajoules of laser energy into the pellet. The resulting fusion reaction yielded 3.15 megajoules out. That is a target gain greater than 1. The yields have scaled rapidly. In April 2025, a nearly identical input of 2.08 megajoules yielded an 8.6 megajoule output, driving the target gain above 4. But an important thermodynamic distinction applies here. Target gain only measures the energy that physically hit the pellet. The massive laser arrays that fired those beams drew vastly more electricity from the local power grid than the 8 megajoules they produced. the actual wall plug energy deficit remains massive. The physics of net energy fusion are now a proven reality. The engineering reality is a steep wall plug deficit that requires entirely new, scaled-up facilities to overcome. Closing that energy gap requires heavy civil engineering. This is the International Thermonuclear Experimental Reactor, or ITER, in southern France. It is an enormous facility, explicitly designed to demonstrate a fusion energy gain of at least 10. ITER is backed by 35 nations. Building a first-of-its-kind megaproject requires extreme precision and heavy supply chain coordination. The cost has risen to 22 billion euros, and the schedule now places the first deuterium plasma operations in 2034. Private startups are running parallel to this timeline, aggressively attempting to build compact devices at a much faster pace. Commonwealth Fusion Systems in Massachusetts has already installed the stainless steel cryostat bases for its Spark Tokamak. Their reactor is built around extremely powerful, high-temperature superconducting magnets, and they are targeting their first plasma for late 2026. These private timelines are attracting serious commercial commitments. Tech corporations like Google and Microsoft have already signed power purchase agreements, contracting to buy megawatts of fusion electricity before the end of the decade. The engineering roadmap has officially bifurcated. We are watching massive, highly methodical international megaprojects race against heavily capitalized, agile private pilot plants. Reaching net energy is only part of the equation. We also have to account for the incredibly hostile environment inside an active reactor, specifically the continuous high-energy neutron flux ejected by the plasma. Fast neutrons penetrate the reactor walls and activate the structural materials. While this radiation does not last for millennia like traditional fission waste, the structural alloys will remain highly radioactive for decades. This creates a strict physical limit. We need advanced plasma-facing components, materials capable of absorbing intense continuous neutron bombardment for 20 or 30 years without structurally degrading. The chemistry of the fuel creates a second major bottleneck. Tritium does not naturally exist in meaningful quantities on Earth. A plant that runs continuously cannot rely on an external supply. It has to manufacture its own fuel on site. This diagram outlines the closed fuel cycle. Engineers surround the plasma core with a tritium breeding blanket, specialized modules packed with lithium. When the high-energy neutrons hit the lithium, they trigger a reaction that breeds new tritium, which is immediately looped back into the reactor to sustain the burn. Scaling a plasma shot into a functioning power plant depends entirely on solving these two variables. The true bottleneck is advanced metallurgy and continuous chemical fuel breeding. When evaluating the timelines of these projects, it is critical to separate the engineering reality from the headlines. The industry measures progress through three highly specific thresholds. Threshold 1 is scientific net energy. This means more energy leaves the burning plasma than the external heating systems put into it. As the NIF proved, this is a milestone we have successfully crossed in the laboratory. Threshold 2 is engineering net energy. This requires the entire facility, the reactor, the cooling systems, the superconducting magnets, and the lasers, to deliver more total electricity to the commercial grid than the plant pulls from it. No experiment or facility on Earth has reached this second threshold. Threshold 3 is economic viability. At this stage, a plant not only produces continuous engineering net energy, but does so at a strict cost per megawatt hour that can compete with existing solar, wind, and natural gas infrastructure. Maintaining a strict taxonomy of these three milestones prevents premature hype. It gives engineers and investors a clear, sober map of where the industry actually stands. Based on the current trajectory of magnet assembly, containment architecture, and fuel cycle development, we can plot a highly credible timeline. The completion of a working pilot plant that delivers actual sustained electricity to a power grid is a mechanically realistic target for the early to mid-2030s. But that 2030s target is entirely contingent on private and public labs successfully demonstrating functional lithium breeding blankets and multi-decade lifespans for plasma-facing components. A single pilot plant proves the concept. Scaling that up into a global fleet of reactors capable of replacing massive chunks of baseload power demand is realistically a post-2040 prospect. This chart tracks the financial confidence behind that timeline. Over $10 billion in private capital has been committed to fusion companies in just the last 5 years, accelerating the pace of development and adding immense credibility to these target dates. The theoretical physics chain, from heating the fuel to achieving ignition, is proven. We are now executing a massive, complex, but strictly solvable mechanical engineering challenge. To bypass the headlines and track the actual hardware being built to cross the engineering net energy threshold, click the link below to access the full technical roadmap.